Welcome back to our lecture series on advanced hydraulics, part of the NPTEL program, phase 2 program. We are in the third module on varied flows. We have finished 10 lectures in this module. Today is the 11th lecture, and by today's lecture, we hope to wind up this module. In the last class, we had discussed on the concepts of spatially varied flow. We had derived the dynamic equation for spatially varied flow for increasing discharge. That is, first using the continuity equation, we identified what is the rate, that is the rate of increase in discharge per unit length, that was identified. It was given by the following expression. Then subsequently, using the momentum equation, we had derived the dynamic equation for spatially varied flow. I hope you recall all the terms here. Y is the depth of flow, S0 is the bed slope, SF is the friction slope, capital Q is the discharge, Q star is the rate of increase in discharge per unit length, G acceleration due to gravity, area A is the area of cross section, again T is the top width of the channel. All these things are self explanatory. Similarly, we had discussed on the dynamic equation for spatially varied flow for decreasing discharge. If there is a continuous decrease in the discharge through a channel, then using the energy principles, we had derived the corresponding equation, dynamic equation. Also, we have suggested how to use numerical methods, that is, numerical methods can be applied to solve these two types of dynamic equations. From solving these dynamic equations, either we can get the depth of flow at various cross sections, or you can get, say, for a specific depth at which cross section it is available, that depth of flow is maintained and all that can be readily obtained. Today, we will be dealing with the concepts on or some of the features on spatially varied flow and its profiles. So, as discussed earlier, the dynamic equation for spatially varied flow in the case of increasing discharge, we had derived it using momentum principles. It was given in the following form. So, if you look closely into these things, this has been given without the momentum corrections applied to the cross section. So, if any cross section is there, then we have taken the average velocity across this cross section as a parameter, and based on that average velocity, whatever correction for the momentum is there, that was not incorporated. We had taken momentum correction factor beta is equal to 1, and we had developed this equation. So, usually the momentum corrections are very much significant in spatially varied flow. Therefore, we have to apply the momentum correction factor, and the improved or modified dynamic equation will look like this. That is, dy by dx is equal to S0 minus SF minus twice beta q q star by G A square, the whole thing divided by 1 minus beta q square t by G A q. So, beta, the momentum correction factor, is incorporated in the dynamic equation. Subsequently, a similar concept, similar principle can be applied for the dynamic equation for decreasing discharge. We had derived it using energy principles earlier in the following form. So, as we have mentioned here also in the cross section, the corrections for energy are not incorporated. So, we need the energy corrections for spatially varied flow, because there is a rapid change or rapid decrease in energy due to the change in flow and all. So, rapid decrease in the sense that some changes in the energy is occurring due to the change in quantity of water and all. So, you need energy corrections also. Therefore, with energy correction factor, the dynamic equation can be specified as given here. Dy by dx is equal to S 0 minus S f minus alpha q q star by g a square, the whole thing divided by 1 minus alpha q square t by g a cube, where your alpha is the energy correction factor. I hope you recall these factors, we had studied them in detail in module 1 and all. So, if you look into both the equations, say dy by the momentum means dynamic equation derived through the momentum principles, as well as the dynamic equation derived through the energy principles, both of them can be written in a common form. So, I have just expressed this thing in a common form here. Dy by dx is equal to S 0 minus S f minus a quantity C 1 into q q star by g a squared by the whole thing divided by 1 minus C 2 q square t by g a cube, where C 1 is equal to twice beta and C 2 is equal to beta when we use dynamic equation for increasing discharge. Similarly, C 1 and C 2 both are equal to alpha when we use dynamic equation for decreasing discharge. So, it is up to you, just for the convenience we have written it in a common form. So, for analyzing the flow profiles in a spatially varied flow, let us first consider through a simple example. So, let me state the example. There is an horizontal rectangular channel that collects water laterally through the overflow spillway. That is, water is entering the rectangular channel through overflow spillway like this. It is entering like this, say maybe from both sides. This rectangular channel has a free fall overfall outlet like this. It is the at the end of this rectangular channel, the water is falling freely. Inflow is uniformly distributed along the channel length. So, the inflow to this channel, it is distributed uniformly at a rate of q star per unit length. Now, derive the equation of flow profile. You can ignore the friction losses. How will you try to obtain the flow profile or the equation for the flow profile? So, this is a very interesting problem. You can see that this is a horizontal channel, means water is coming into this channel. The length of the channel, let us assume it as capital L. Then the width of the rectangular channel is capital B according to our normal convention. Depth of flow at any location, it is y, right. So, based on this, how will you obtain the flow profile? So, again the cross section, we have our rectangular channel, B is the width, y is the depth of flow. So, B and T both are same for the rectangular channel. Now, read the question carefully. What are the assumptions or what are the things given here? There is an assumption that you can ignore friction losses. So, what does that mean? While ignoring friction, to ignore friction losses means you are considering S of is equal to 0. Another criteria given is this is a horizontal rectangular channel. So, that means your bed slope is also equal to 0. Therefore, your dynamic equation now this becomes dy by dx is equal to both S 0 and S of r 0. So, minus 2y's, okay. I am just taking the common form. Okay. Is it sufficient? Common form of the thing. So, minus, or let me say as this is a case of increasing discharge. So, let us see. So, this becomes minus 2 q q star by g a square, the whole quantity divided by 1 minus q square t by g a q. We are assuming that the momentum correction factor, it is approximately 1 for only for this particular problem, we are assuming that situation. So, just go through here. So, from here starting on from here, the water is collected in this channel and it is flowing like this. So, at a rate of q star it is being collected, the entire thing. So, we can suggest now for the rectangular channel V is equal to T for rectangular channel, A is equal to B y, right. What is, let me ask you a simple question now. Okay, I will just redraw the thing here. So, this is the horizontal channel. We are looking the longitudinal profile. So, the flow in the channel, it is having a free outfall. Okay. So, I will just redraw the thing again like this. So, in this case, what will be the depth of flow at the free fall outlet? This should be equal to the critical depth. It should be equal to the critical depth in the flow. So, if that is clear to you, then discharge at free fall outlet. What is the discharge at free fall outlet? If you recall the thing, we had suggested that water is slowly increasing. Water is slowly increasing from this section to this section as it goes downstream. So, the rate of increase is q star per unit length. So, we give the quantity q 0, this is nothing but q star into the length of channel. So, this q 0 is the discharge at outlet, or you can suggest now that q star is nothing but equal to q 0 by L. Also, for any small elemental length in the channel, say dx, you can easily identify the change in discharge dq. This is nothing but equal to q star into dx. So, this quantity now it can be easily suggested, you can integrate this thing dq is equal to into q star dx, or you will find that discharge at any section along the channel, q, this will be nothing but equal to q star into x, because q star is independent of length x. So, therefore, you can take it out and integral dx will give you x. So, we will use the same relationship. So, we know that average velocity at any section, this is nothing but discharge divided by the area of flow, or q is equal to v bar a. These things you have been dealing it earlier onwards. Now, q is equal to q star into x. Therefore, your average velocity becomes q star into x divided by area. For this rectangular channel, v bar is nothing but q star x by b y. So, what do you get from this thing? Substitute these quantities in dynamic equation. So, dy by dx is equal to minus twice capital Q is q star x. So, this becomes q star square x by b y, I beg pardon, this becomes q star squared x by g b squared y squared, the whole thing divided by 1 minus q star squared into x squared b by g b cube y cube. So, we have just substituted all the quantities. You know what is q. So, q is equal to q star x, that is substituted here. Instead of the top width t, we have substituted the width b, and we got this. So, you can cancel out some of the terms and all here. You will get the following equation. I am just working out for your benefit, showing the working procedure here. So, your dy by dx will now become minus twice q star square. Sorry, I am just rubbing and writing it again it is not clear in the screen here. So, minus twice q star squared x y by g b squared y cube minus q star squared x squared. You can just inverse this relationship. Dx by dy is equal to q star squared x squared, because minus is already there. So, I am just writing as per convenience 2 y's q star squared x y. So, again, how can you write these things? I am just splitting the entire portion now. See, dx by dy is nothing but equal to, this is x by 2 y minus g b squared y cube by, sorry, this is g b squared y squared by 2 y's q star squared x. So, when you get such an expression, you can just again look into the thing. You can just take 2x quantity into the numerator of the left hand side. I am just taking it like that. So, 2x dx by dy is equal to, see, there was no x in the denominator in the here in the first expression on the RHS. So, I have to take into account. So, this becomes x squared here, x squared by y minus g b squared y squared by q star squared. So, what is 2x dx? What is this quantity 2x dx, dx by dy? Just go through your basic mathematics and all. So, I will write this quantity as d by dy of x squared by, sorry, d by dy of x squared equal to x squared by y minus g b squared y squared by q star squared, or this can be written according to the standard form of differential equations. So, d by dy of x squared is minus 1 by y into x squared is equal to minus g b squared y squared by q star squared. So, here x squared is the dependent variable in the differential equation. X squared is the dependent variable and it is getting differentiated with respect to y, independent variable. So, if you solve this equation, you will get x squared as some function of y. This is how the objective of solving a differential equation should be. So, the same phenomenon is adopted here. We will get, say, an expression x squared is equal to some function of y based on the boundary conditions. So, you know the boundary conditions for the channel. Water is flowing out like this, So, this depth we suggested that this is at length, at x equal to length you have depth is critical, your depth is critical. So, y c, let me write it as y c. How do you identify the depth, critical depth y c? Because you know the discharge at outlet q 0 or q c also you can write. Q 0 is nothing but equal to q star into L. This you are quite aware, that is the discharge at this outlet. So, based on that, based on these quantities, you can easily identify what is the critical depth y c. So, based on this critical depth at x is equal to L, y is equal to the critical depth y c, use that condition is applied. All these conditions on incorporating, you will get the following expression for x. X by L whole square is equal to 3 by 2 y by y c minus half of y by y c whole cube. This expression we will get on solving the thing, applying appropriately these conditions. Some scientists have tried to obtain, if you recall in the gradually varied flow, we had a well distinguished flow profiles, say mild slope, steep slope, horizontal, adverse, all those conditions were incorporated and we had various kinds of gradually varied flow profiles. Unfortunately, in the spatially varied flow, a well defined categories are very much limited. Only very few scientists have worked on that and they have come up with certain strategies. For example, the scientist Lee in 1955, he performed certain analysis on spatially varied flow. Say in the last example on the rectangular channel, it was a horizontally varied, it is a horizontal rectangular channel. So, the bed slope is 0. Lee had performed experiments for spatially varied flow in sloping beds. So, maybe consider the same type of rectangular channels itself or the parallel, the walls are parallel and all. If you consider that things into account, let us try to investigate what are the properties or features that can be seen in spatially varied flow. If you recall Froude number, the Froude number, we had suggested that Froude number is equal to q squared by g a squared y, or this is equal to v squared by g y, or sometimes we may write this as Froude number f r is equal to v by root of g y. So, this was giving you certain principles or certain quantities on how, due to change in inertia and gravity, or how the inertia is affecting, means how the motion of the body is being affected by inertial and gravitational forces and all. That relationship is being described to the Froude number. We had described it in the critical flow module 1 and on Froude number. For critical flow, if you recall them, Froude number should be equal to 1. So, this Froude number concept we are again trying to utilize here. So, the Froude number at critical flow in the rectangle in the same type of rectangular channels. We can now suggest that q squared L squared by G A squared Y C is the critical depth. This should be equal to 1. Now, for any depth along the sloping rectangular channel, say this is a sloping rectangular channel, here lateral increase is there in the flow of water. So, we do not know how, whether it will increase like this or whether it will decrease or whatever be, and it is, say it is having a outlet, this portion is the outlet of the channel. So, this outlet, it may be either having a free outflow like this, or it may be sometimes jumping to some other, means if water is already there in the downstream, it may be jumping, or it may be getting stagnated like that at that level without any jump. So, we do not know the situation. Based on this, Lee in his analysis, he suggested that the fluid number at any section, it can be given as q star squared x squared by G A squared y. So, when he gave this quantity fluid number F r squared is equal to q star x squared by G A squared y, this quantity subsequently, with this quantity he related with another parameter, another hypothetical parameter he suggested. He suggested a hypothetical parameter, say J. J was defined as the bed slope into length of the channel divided by the critical flow. So, we are assuming that at this brink the flow is critical, this is the length of the channel. With these things in picture, he defined a parameter J is equal to S0 L by Y C and try to compare F r with J. He came with amazing profile. So, although we do not have data and all, we have not plotted these things in scale. We are just simply trying to introduce you the concept. So, with fluid number on the y axis and the hypothetical parameter J on the x axis, they have identified that there are 4 main regions of fluid flow. Say this is this is a particular region where I can suggest that this is region A. Here they have suggested that J is equal to 2. From that point onwards, this is being suggested. Another region he had identified, and this is region B of fluid flow profile. Then a third region was suggested, region C, and this is region D. Like these 4 regions were identified for the spatially varied flow. So, your spatially varied flow can occur in any of these regions. It can be in region A, or it can be in region B, region C, or region D. In the region A, it is considered that flow is always subcritical. Flow is always subcritical. So, the critical flow depth line, it increases from the starting of the channel. Say if it is starting like this, from here, even the critical depth line increases like this, and your flow is always subcritical. Okay. That is, the depth of flow is always above the critical flow depth line. Like this, the flow can occur. If that is being shown, if this type of flow exists, such type of spatially varied flow is considered in region A. In region A, the property is that the slope of the fluid number dFr by dx, this is always greater than 0. So, the depth of flow is always greater than the critical depth, that is also being suggested. Region B. In region B, what happens is that say if this is the critical depth line, again the flow is subcritical throughout. Now, the assumption here is that it will first increase, then it may decrease like this. The depth of flow, it may first increase, then it may decrease. So, fluid number in this case, the fluid number first increase as the flow proceeds downstream, then it reaches a maximum value almost near to unity, then it decreases. They have identified that this J is almost equal to 1 plus fluid number at the critical section. So, at this location, this J, you can separate region B with respect to region C. Similarly, region C and region D, they are also defined. Region C represents in the graph this region C, it represents the condition at which there is supercritical flow in downstream portion and a hydraulic jump occurs in the channel. Region C, that is a supercritical flow occurs in the channel. So, this is the channel bed. Your flow maybe something like this. It is below the critical depth, and from here it causes a jump and flow like that. So, this is one type of situation that can be encountered in such channels. Due to the supercritical conditions and all, it is considered in another region. So, it is considered as in a region defined as region C and all. Region D also similar, in a similar form, instead of a hydraulic jump, it will be purely merging with the water profile there existing in the downstream. So, without hydraulic jump. So, that is how region D is also defined. As we according to our these things and all, we are not interested to cover much deeper in these portions and all, and moreover this module has taken more lectures also. We try to minimize the portion here. So, again look, come back into the spatially varied flow dynamic equation. So, you have dy by dx, this is equal to S0 minus SF minus C1 into QQ star by GA square by 1 minus C2 Q square T by GAQ. So, this I can just write it in a convenient form as 0, I am taking it out, 1 minus SF by S0 minus C1 into QQ star by GA squared S naught. The whole thing divided by 1 minus C2 into Q square T by GAQ. So, recall the module 1 and module 2 portion. We had defined discharge with respect to conveyance factor, various conveyance factors and all, we had described them. So, using the conveyance factor, Q is equal to K SF to the power of half. K is the conveyance factor K, SF is the friction slow, if you remember them. So, this is the actual discharge. You can also give normal discharge using the bed slope. So, it is nothing but K as 0 to the power of half. It is for a given depth, what is the normal discharge that can be identified? What is the normal discharge for a given depth? That is that given depth can become a normal depth using conveyance factor K and bed slope as the parameter. Also, recall the critical flow. The critical flow QC, it can be given as GAQ by C2T to the power of half. Here we have incorporated the correction factor. That is why C2 is coming into picture here. Earlier C2 was not there, we have taken correction factors as unity and all. So, if the based on this thing substitute it in the equation for dy by dx, you will get dy by dx is equal to S0 into 1 minus K squared by Q squared, K squared by Qn squared, SF squared is written like this, S0 squared is written like this, minus Q squared by Qn squared C1 times K squared Q star by GA squared Q. I hope you are able to understand. If you recall that here in the denominator in this expression S0 is coming into picture, S0 is coming into picture, therefore, Qn term is also coming there, and as S0, for obtaining S0 you require Qn squared term. We are multiplying both the numerator and denominator by Q in this expression. That is for here it is Q squared and here it is Q. This whole quantity divided by 1 by Q by QC whole square. It is in a similar form as you have done for the dynamic equation for gradually varied flow and all. Almost in a similar way, we are writing the expressions. So, now 1 minus Q by Qn whole square 1 plus C1 k squared by Ga square Q square by Q, the whole thing divided by 1 minus Q by QC whole square, like this we get. So, we can, if you just look back the thing, if you just look back into this expression and if you recall the gradually varied flow dynamic equation and all, in a similar way some quantity can be decided. This, instead of writing Q by Qn whole squared into 1 plus C1 Q square k squared by Ga square Q star by Q, we can define a pseudo normal discharge Qn1 something like that, where this is nothing but equal to the normal discharge that would have been for that corresponding depth Qn divided by root of 1 plus C1 k squared by Ga square Q star by Q. Like this you can easily define the thing. So, this normal depth, if you can identify that this normal depth, you can use in further analysis. For identifying transitional depth or transitional profile and all. Transitional depth and transitional profiles. So, this way the things are described here. As I mentioned earlier, we will not go further into more aspects of the spatially varied flow. If time permits, we may come back again later in the final modules and all and see that spatially varied flow can be further covered or not. With this way, we would like to wind up this module. We can have a brief quiz also for today's lecture. The quiz question, I can just dictate it now. So, the first question, what is fluid number? What is the fluid number at the free fall outlet for a rectangular channel? What is the fluid number at the free fall outlet for a rectangular channel? This is the first question. And your second question is, for the rectangular channel having increasing discharge, if the bed slope and friction slope are same, what will be the dynamic equation for spatially varied flow? That is, for the rectangular channel having increasing discharge, if your bed slope and friction slope are same, what will be the dynamic equation for spatially varied flow? So, the solution for the first one, what is fluid number? I hope you all know that. we have been studying this, we have taken means in many of the modules these are coming into picture. In many branches also fluid number is being taught. Fluid number Fr, this is nothing but velocity by root of g and product root of g y, that is y is depth of flow, v is average velocity in a section. So, based on these things we have derived fluid number. So, what is the fluid number at the free fall outlet for a rectangular channel? If you have a rectangular channel like this, if you have a rectangular channel, and the water is having a free outfall. So, the depth of flow here, this will be critical depth, right. So, fluid number will be equal to 1 at critical depth. So, for your question the fluid number will be 1. Next question, for the rectangular channel having increasing discharge, if bed slope and friction slope are same, what will be the dynamic equation for SVR? Just write for the increasing discharge dy by dx is equal to S0 minus SF minus 2 q q star by g v squared y squared by 1 minus q square t by g a q or g b q by q. That also you can write it like that. Now, you know that this quantity t is same as b. So, like that this expression, what happens now? Dy by dx, if S0 is equal to SF, then dy by dx is equal to minus 2 q q star by 1 minus q squared by g b squared y cube. This will be your expression for dynamic equation. So, this way we are winding up this module. In the next lecture we will be taking the new module on rapidly varied flow. Thank you.